Welcome back. In this lecture video, we're going to be looking at example 5.2 in the notes, which again involves a 2 by 2 complete factorial treatment structure. So let's look at a description and an overview of the context of the example. So again, consider a 2 by 2 complete factorial treatment structure. The two fixed effect factors under consideration will be denoted as by factors A and B. This 2 by 2 complete factorial treatment structure consists of 2 times 2 or 4 treatment combinations, which are denoted by A1B1, A1B2, A2B1, and A2B2. Note that every level of each factor occurs in combination with every level of the other factor. And so this is indeed a complete factorial treatment structure. Now suppose that the 4 treatment combination means are as given in the two-way table on the following slide. And so here we have that. And so the mean of the treatment combination A1B1, which is denoted by mu11, is 50. The mean of the treatment combination for A2B2, which is denoted by mu12, is 100. The mean of the treatment combination for A2B1, which is denoted mu sub 21, is 100. And the mean of the treatment combination for A2B2, which is denoted by mu sub 22, is 50. So these are the treatment combination means, and we're going to be calculating various means and effects as we did in the previous example for this particular situation. Now recall that in the means model representation, if the treatment means mu sub ij are fixed effects, then the mu ij's, they're unknown constants, and the arithmetic mean of their values is equal to mu, the overall treatment mean, which is calculated in several ways. And we've shown those calculations here. And in addition to denoting this overall treatment mean by mu, or the overall mean of the treatment combinations as mu, we can denote this as mu bar dot dot if we want to emphasize how we're actually calculating this and the fact that it is the arithmetic mean of the various treatment combination means. Also recall that in the effects model representation, which involves the various treatment effects and their interaction, the alphas, the betas, and the alpha beta ij's, if the treatment effects are fixed, then the following constraints hold among the various parameters. So the sum of the alpha parameters is 0. The sum of the beta parameters is 0. If we sum the alpha beta ij's along the first index, along the I index, then that sum is 0. And in addition, if we sum the alpha beta ij's along the second index, the j index, then that sum is 0 as well. And obviously the implication of those last two bullet points, those last two constraints, would be that if we sum the alpha beta ij's over both indices, then that would be 0 as well. Now, in the previous example, example 5.1, we were given the values of the alphas, the betas, and the alpha beta ij's, but in this example, we're not. We're given only the treatment combination means. What I want you to do as an exercise is to use the given values of the treatment combination means along with the constraints among the various effects model parameters and do the following. Calculate the arithmetic mean of the treatment combinations, which is mu, or also denoted mu bar dot dot. And in addition, calculate the various effects model parameters, alpha 1 and alpha 2, beta 1 and beta 2, and the various alpha beta ij's. So do that as an exercise. And you'll probably have to do that on an exam, so make sure that you can do that. And it's not that hard. You just take the values of the treatment means along with the various constraints on the parameters, and you should be able to come up with these values. Now we're going to proceed by calculating various means and effects associated with this treatment structure. And in doing that, we're going to use the formulas, but we're also going to do this in the context of our two-way table. And so we will be expanding the table, augmenting it with rows and columns to facilitate these calculations and to have places to put the various means and effects. And so we will start off first by calculating some means. And so we're going to be calculating arithmetic means for each factor level, as well as the overall mean of the treatment combination means. And let's start off by calculating the row means. These are the means of the levels of factor A. And so mu bar 1 dot is the mean of the first level of factor A. And the two treatment combinations at that first level of factor A have means of 50 and 100, and so when we average those values, we get 75. Mu bar 2 dot is the mean of the second level of factor A, and the treatment combinations that have that second level have treatment combination means of 150, and so again, when we average those two values, we get 75. And we can see these calculations in the context of the table. You can see here I've added a column here on the right that is going to contain the means of the two factor levels for factor A. And so 75 is the mean of 50 and 100. That's the mean of the first level of factor A. And then the mean of the second level of factor A is again 75, being the mean of 150. Next, we're going to calculate the column means, the means of the levels of factor B. And so the mean of the first level of factor B, mu bar dot 1, is the mean of 50 and 100, so 75. The mean of the second level of factor B, mu bar dot 2, is the mean of the values 150, and so that again is 75. And so we see these calculations in the context of the table. The mean of the first level of factor B is the mean of 50 and 100, and that value is 75. And then the mean for the second level of factor B is the mean of the values 150, and again that averages to 75. And then finally we're going to calculate the overall mean, and as before we can calculate the overall mean in three different ways. First, as the mean of the column means, the arithmetic mean of the means of the levels of factor B. That's the first expression. We can also calculate the overall arithmetic mean of the treatment combinations as the arithmetic mean of the row means. In other words, the arithmetic mean of the means of the levels of factor A. That's the second expression. And then finally, we can calculate the overall arithmetic mean of the treatment combination means as the arithmetic mean of all four treatment combinations together, and that is the third expression. And then we can denote the overall treatment combination, the overall arithmetic mean of the treatment combinations as mu, but if we want to emphasize the fact that, or how we're calculating it, we can denote it by mu bar dot dot as well. And so we have all of these values. We have the four treatment combination means, which were given in the statement of the example, and we've just previously calculated the column means as well as the row means. And so we have all the ingredients we need to calculate the overall arithmetic mean of the treatment combinations using either or any of these three formulas, and in this case that overall arithmetic mean of the treatment combination means is 75. And so looking at the table here, we can demonstrate all three ways of calculating the overall arithmetic mean as the mean of the column means, as the mean of the row means, and also as the mean of the individual treatment combination means. Next, let's look at the various types of effects that are available to be considered and calculated in the context of a 2x2 complete factorial treatment structure. You'll recall that in this context there are three types of effects. We have simple effects, main effects, and interaction effects. There are four simple effects that we can calculate and consider. There are two main effects, and then we have an interaction effect. And as in the previous example, we can think of the interaction in two different ways, but it's going to turn out that those are equivalent and they are therefore numerically equal. And so we say that there's one interaction between the two factors A and B. So let's first calculate the simple effects. All right, and so as a reminder, the simple effect of a factor is the difference between treatment means for two levels of that factor at a given level of the other factor. And so in the notation of the means model, the simple effects are calculated in the following way. The simple effect of A at B1 is mu21 minus mu11, the difference between the treatment means for those treatment combinations that have level B1. And so 100 minus 50, and so that turns out to be 50. So the simple effect of A at B1, the first level of B, is 50. And we can demonstrate this calculation in the context of our table, where I've augmented the table with rows and columns for the simple effects of A and the main effect of both, the simple effects of A, the simple effects of B, and the main effect for each of those two factors. And right now we're working on the simple effects of A and B, so let's focus on that. And so we can see that the simple effects of A, by definition, the difference between the treatment combinations at the first level of B1. All right, and so 100 minus 50, which is 50. The simple effect of A at the second level of B is mu22 minus mu12. So in this case, 50 minus 100, and that's going to be negative 50. And we can also demonstrate this in the context of our two-way table. So the simple effect of A at the second level of B, B2, is the difference in the treatment combination means that have received level 2 of B. So in this case, 50 minus 100, or negative 50. Next, let's calculate the simple effect of B at the first level of factor A. And so that, by definition, is mu12 minus mu11, which is 100 minus 50, or 50. And so we see this as the difference between the treatment combination means that have for the treatment combinations that have received the first level of factor A. And so that difference is 100 minus 50, or 50. And then finally, the simple effect of B at the second level of A, so at A2, is by definition mu22 minus mu21. That would be 50 minus 100, or negative 50. And so demonstrating this calculation in the context of the table, we would be taking the difference between the two means for the treatment combinations that have received the second level of factor A. So 50 minus 100, that gives us negative 50. And then finally, we can calculate the simple effects using the effects model parameters and their values as well. Now, again, these effects model parameters, their values were not given to us in the statement of the example, I'm wanting you as an exercise to calculate their values. And so once you do that, then plug them into these four formulas and verify that you get the same values as we got in using the previous or using the other calculations. And so make sure that you get these values that I've highlighted here in the table. All right, next let's calculate the main effects for A and for B. And so recall that the main effect of a factor can be defined and calculated in two different ways. First, we can define and calculate the main effect of a factor as the arithmetic average of the simple effects of that factor. We can also define and calculate the main effect of a factor as the difference between the means of the two levels for that factor. Now, in the notation of the means model, the model effects are represented as follows. So on the left-hand side of each equation, I have the representation given by the arithmetic average of the simple effects of that factor. And on the right-hand side of each equation, I have the representation which is the difference between the means of the two levels for that factor. And so let's first calculate the main effect of factor A. And let's first use the calculation, which is the arithmetic average of the simple effects of factor A. And so the two simple effects of factor A are mu21 minus mu11 and mu22 minus mu12. So again, mu21 minus mu11 is the simple effect of factor A at the first level of B. Mu22 minus mu12 is the simple effect of factor A at the second level of factor B. And so we average those two values, and that will give us the main effect of A. Now, the two simple effects of factor A were 50 and negative 50, and so when we average those, we get 0. All right, and so in the context of the table, we can demonstrate this calculation by averaging or calculating the mean or the arithmetic average of the simple effects of A. And so we're going to calculate the arithmetic average of 50 and negative 50. And again, that gives us 0. We can also calculate the main effect of A as the difference between the means of the two levels of factor A. So mu bar 2 dot minus mu bar 1 dot. All right, and so those would be, that would be the difference between the row means for A2 and A1. So 75 minus 75, that gives us 0. And we can demonstrate this calculation in the context of our two-way table, all right, by taking the difference between the row means for A2 and A1, 75 minus 75, which again gives us 0. And we can see here that the two calculations for calculating the main effect of A both give us 0, as they should, because they are algebraically equivalent. All right, next, let's calculate the main effect of B first as the arithmetic average of the simple effects of factor B. So the simple effects of factor B are mu12 minus mu11 and mu22 minus mu21. Mu12 minus mu11 is the simple effect of factor B at the first level of factor A. Mu22 minus mu21 is the simple effect of factor B at the second level of factor A. Those two simple effects were calculated previously and found to be 50 and negative 50. Those two values average to 0. And so, based on this calculation, the main effect of B is 0. And that's shown here in the context of our two-way table. The main effect of B is the mean of the simple effects of B, the simple effects being 50 and negative 50. And so when we average those, again, we get 0. And then we can calculate the main effect of B as the difference between the means of the two levels of factor B. So mu bar dot 2 minus mu bar dot 1. Those are the column means for the levels of factor B. And those two values were both 75, and so their difference is 0. And again, we can demonstrate this calculation in the context of our two-way table. And so you can see here that we're on the right-hand side. In the column main effective B, we are calculating the main effective B as the difference between the two means of the factor levels of B. So the two column means, 75 minus 75. And again, that gives us 0. So both methods give us the same value, which is a good quality control check when we do our calculations. We know that they need to be equal because the expressions are algebraically equivalent. And in doing these calculations and filling out this table as we're doing, it's a good way to check our work and make sure we're doing the calculations correctly. All right, and then in the notation of the effects model, the main effects can also be calculated using the formulas given below. And so the main effect of A can be calculated as alpha 2 minus alpha 1, and the main effect of B can be calculated as beta 2 minus beta 1. Now, if we're given the alphas and the betas, we can use these formulas to calculate the main effects of A and B. But again, we were not given those values in this example. As an exercise, I want you to calculate those. And so once you've done that, I want you to, once you've found those values, I want you to make sure that you get the same values for the main effects of A and B that we got in filling out the table. So you should get these values here. But let me also say that if you know what the main effect of A is and you know what the main effect of B is, that knowledge, knowing those values, can help you calculate the values of alpha 1 and alpha 2, as well as, and also beta 1 and beta 2. Because remember, there are constraints on alpha 1 and alpha 2. There are constraints on beta 1 and beta 2. And so all of these constraints help you to figure out what their values are once you've been given some of the other values. All right, and then finally, let's calculate the interaction effects for this situation. And as we did in the last example, we've reserved a space in the table for the interaction effect. It's that bottom right-hand corner of our table. All right, and you'll recall that the definition of an interaction effect, the interaction of one factor with another factor, can be computed as the difference between the simple effects of the first factor at each of the two levels of the other factor. So while a main effect is an arithmetic mean of simple effects, an interaction is a difference of simple effects. And so in particular, the interaction of A with B, so thinking about it from this perspective, the interaction of A with B, that by definition is the difference between the simple effects of A at the two levels of B. And so the two simple effects of A are mu2, 1 minus mu1, 1. That's the simple effect of A at the first level of B. And mu2, 2 minus mu1, 2. That is the simple effect of A at the second level of B. Those two simple effects were found to be 50 and negative 50 respectively. And so when we take their difference, we get 100. All right, and we can show that calculation in the context of our two-way table. And so the interaction effect of A with B is, by definition, the difference between the simple effects of A at those two levels of B. And so 50 minus negative 50. And so again, that gives us an interaction effect value of 100. All right, now we can also calculate the interaction of B with A, and by definition, that is the difference between the simple effects of B, and so the two simple effects of B are mu1, 2 minus mu1, 1. that is the simple effect of b at the first level of A, and mu22 minus mu21, that is the simple effect of b at the second level of A. Those two simple effects were found previously to be 50 and negative 50 respectively. And so when we take the difference, we get 100. And recall that, I've asked you in a previous lecture video to demonstrate that in a 2x2 complete factorial treatment structure, I've asked you to show in general that the interaction of A with B is equivalent to the interaction of B with A, and so they will be numerically equal. In this example, since we actually had numbers for the treatment combinations, and we can calculate all these things, what I'm wanting you to do, what I'm wanting us to do in this example is to verify that the two ways of looking at this interaction produce the same number, and they do. They both produce a number of 100. Okay, and so this particular way of looking at the interaction of B with A, is demonstrated on this slide in the context of our table. So the difference between the simple effects of B at A1 and A2, so 50 minus a negative 50, and that gives us, again, a value of 100. And so again, we have verified that numerically, in this example, that the two ways of looking at the interaction produce the same value, the value of 100. And so we see that we can calculate it either way, either as 50, either as a difference of the simple effects of A or as a difference in the simple effects of B. So 50 minus a negative 50 as the difference in the simple effects of A in this case, and it's actually the same difference when we look at the simple effects of B. So the interaction effect for this particular situation, given these values for the treatment combination means, the interaction effect is 100. Now here is an interaction plot showing the treatment combination means. And again, I'm using the horizontal axis as a qualitative axis, a place to put the two levels of factor A. And then I'm using color to differentiate the two levels of factor B. And then the vertical axis is a quantitative axis with respect to which I am plotting the treatment means, the values of the treatment means for each of the four treatment combinations. And we can see here that not only are the lines not parallel, but they actually cross. And this is obviously a contrived example to demonstrate some things here. But we can see here that because these lines are not parallel, there is obviously interaction between factor A and factor B. And you'll recall that in the last lecture video we said that if the lines are parallel, that indicates no interaction. Parallel lines would indicate that the effects of the factors are additive on the response. And if the lines are not parallel, that indicates interaction exists. And the extent to which the lines are not parallel, that indicates the degree of interaction. So these are very, very non-parallel lines, and so there's a lot of interaction here between the two factors. Now, let me also just say here that we're not dealing with data here. We're not dealing with data that's subject to error. These are idealized examples. These are examples where we're actually given the true values of the treatment combination means. And so there's no uncertainty with regard to the values in this interaction plot. And there's no uncertainty with regard to whether or not the lines are parallel. In a real situation where we're basing our assessments on data, then there's going to be uncertainty with regard to our estimates of the treatment combination mean values. There's going to be uncertainty then associated with the lines in the interaction plot And so in order to evaluate whether or not there's interaction, in many cases, we're going to have to rely on something more than just the plot. We're going to have to rely on formal hypothesis tests. In some cases, it will be obvious that there is interaction. For example, if we had an interaction plot based on real data that looked like this, then it would be almost a sure thing that the formal test would indicate that interaction exists. But if we were dealing with a real data situation where the lines were almost parallel but not quite, then we really could not make a determination based solely on the interaction plot. We would have to base that assessment on the formal hypothesis tests. So these examples that we're looking at now, example 5.1 and now 5.2, again, we are dealing with, assuming that we know the value of the treatment combination means, and we're doing this for, illustrative purposes to show the various values, the means and the effects that are calculated that follow from those treatment combination means. And in the future, in a future lecture video, at some point, we're going to be looking at real data, and we'll also, and so we'll have to start estimating those treatment combination means. Okay, so assessing the effects of the factors in the presence of interaction. So when we have strong interaction, so in this example, okay, given these treatment combination means, we've got a lot of interaction. The value of the interaction effect is 100, all right, and we see here that in the interaction plot, the lines are not only not parallel, but they cross, and so that indicates that we've got a lot of interaction here. And so how can we assess the effects? How are we to assess the effects of the factors in the presence of interactions like this? And even if the interaction is not that strong, how should we interpret the effects of the factors? And so this example demonstrates the care that must be taken in interpreting model effects in the presence of interactions. So let me just go back a few slides here and again point out that based on these treatment combination means, notice that the main effect of A is 0 and the main effect of B is 0. Now, if we had just looked at the main effects of the factors, and that's it, we would have concluded that neither factor affects the response, since each of the factor main effects is 0. But this is very, very misleading. Each factor does, in fact, affect the response, but the effect of each factor depends on the level of the other factor making up the treatment combination. In particular, at level B1 of B, the first level of factor B, the effect of A2 relative to A1, that is, the simple effect of A, is an increase of 50 units in the mean response. So we see that, for units, experimental units that would get the first level of factor B, B1, going from A1, or the difference between those that get factor level 2 of factor A versus level 1 of factor A, that's a difference of 50 units in the response. That is the simple effect of A. On the other hand, at the second level of factor B, B2, the effect of A2 relative to A1, that is the simple effect of A, is not an increase but a decrease in the response of 50 units in the mean. All right, and so we see that here. At the second level of factor B, the impact of the factor A, so A2 relative to A1, is a decrease from 100 to 50 units. So that's a decrease of 50 units. So the factor A is impacting the response. Even though the main effect of A is 0, all right, in this example, factor A is impacting the response. Just it's impacting it in different ways depending upon the level of factor B that we're talking about. Likewise, at the first level of factor A, A1, the effect of B2 relative to B1, which is the simple effect of B, is an increase of 50 units in the mean response. And so we can see that here at the first level of factor A, the impact or the effect of factor B2 or factor level B2 relative to B1 is an increase of 50 units. But at level A2 of A, the second level of factor A, the effect of B2 relative to B1, which is the simple effect of B, is a decrease, not an increase, but a decrease of 50 units in the mean response. And so we see that demonstrated here. All right, at the second level of factor A, the impact or the effect of B2 relative to B1 is not an increase of 50 units like it was at the first level, but a decrease. All right, and so that simple effect is negative 50. So factor B, even though factor B has a main effect of 0, which if that's all we looked at, we would say, well, factor B must not be important because its main effect is 0. Well, that's completely untrue. We see that factor B does impact the response. It just impacts it differently depending upon which level of factor A that we're talking about. And this example was constructed in such a way that the impact of factor B at the different levels of factor A offsets each other. And so that's why we get a main effect of B. And the same thing for factor A. All right, the impact of factor A, depending upon which level of factor B we're looking at, they offset each other. And so that gives us a main effect for A of 0. And so this shows that a very important result. Interpreting factor main effects is somewhat meaningless and in fact can be quite misleading when interactions exist between those factors. When a factor is involved in interactions with other factors, the general recommendation is that no attempt should be made to interpret the main effect. And in fact, the main effect should not even be reported to prevent misinterpretation by readers. Instead, the focus should be on reporting and interpreting the simple effects for that factor. Let me say that again. Interpreting factor main effects is meaningless and in fact misleading when interactions exist between those factors. When a factor is involved in interactions with other factors, no attempt should be made to interpret the main effect, and in fact, the main effect should not even be reported. Instead, the focus should be on reporting and interpreting the simple effects for that factor. All right, so that is the end of this example. In the next lecture video, we're going to look at one more example of a 2x2 complete factorial treatment structure.